Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, welcome to Technical Session 11E. My name is Amog Dhamdere, and I will be moderating this session. On behalf of the entire team of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome all of you to the 11th edition of the International Congress on Information and Communication Technology, ICICT 2026. The 11th edition of this conference is being organized in hybrid mode, and the physical event was held yesterday in London, and the virtual event is being held through Zoom from the 25th to the 27th of February in 2026. I hope all of you will enjoy the knowledgeable and interactive sessions we have planned throughout the day today. In this particular session, we will be having 6 presentations, and each presenter will be given 12 minutes for their presentation, and then 3 extra minutes for questions and answers. On the completion of 10 minutes, I will be raising a gentle reminder. And there is another request to all the participants that all of you please stay connected with us until the closing remarks are given. And if you have any queries or updates, you can write it to me in the chat box. Now, before we begin, I would like to introduce our session chairs for this session. So our first session chair for today is Dr. M.A. Vakchure. Dr. Vakchure is an associate professor and PG coordinator in the Department of Computer Engineering at the Amrit Vahini College of Engineering in Sangamner, Maharashtra. He has over 17 years of teaching experience and specializes in data mining, business intelligence, and information retrieval. His academic and research contributions focus on data-driven decision-making and advanced. Welcome you, and I request you to give us your opening remarks.
Thank you, sir. So, very nice to join this particular conference, ICICT 2026. That is International Conference on Information and Communication Technology, organized in between 24 to 27 Feb. So, all the best to all the paper presenters from my side, and all the best for your conference. Thank you.
Thank you so much, sir. Our next session chair is, excuse me, just a second. So our next session chair is Professor Mauricio Junior Santa Maria Ruiz. He is a professor and researcher at the Universidad de la Costa in Barranquilla, Colombia, where he currently serves as an editorial coordinator. His research focuses on social sciences and business management, with particular interests in human talent management, innovation and marketing, and agricultural value chains. We welcome you, sir, and I request you to give us your opening remarks.
Hi, it's a pleasure to be with you. Hello, I would also like to introduce myself. I would be Assistant Professor Mauricio. I work with him also in the University of the Coast. I have done research with him, and I also belong into his seminar studies.
Well, it's very good to have you. Well, we can now proceed with our presentations for today. So our first presenter would be Chimuka Munde from the University of Zambia. And the title of the research paper is An Edge-Centric IoT ML Framework for Early Vandalism Detection and Predictive Maintenance of Power Distribution Infrastructure. Sir, I request you to kindly unmute yourself and start presenting.
Good morning, good afternoon, panelists. Let me just share my screen. I believe my screen is visible.
Yes, sir, your screen is visible and you are audible as well, so you can start.
Thank you so much. My name is Chinkamonde, and today I'll present my research titled as shown on the screen. This is the format that the presentation will take. Power distribution systems in many developing regions face persistent vandalism, including transformer tampering, copper theft, and unauthorized substation access. These coordinated attacks cause sudden outages, prolonged restoration times, financial losses, as well as significant deterioration of grid reliability. They also weaken public confidence in utility providers. Traditional countermeasures such as manual inspections, physical security are reactive, difficult to scale, and ineffective for geographically dispersed infrastructure. Advances in IoT and machine learning have significantly strengthened predictive maintenance by enabling early detection of technical faults through condition monitoring data. However, predictive maintenance systems are primarily designed to identify gradual equipment deterioration rather than sudden malicious intrusions, creating a security gap. Furthermore, many IoT-based security solutions depend on continuous cloud connectivity, energy-intensive vision systems, or centralized analytics, limiting their applicability in low connectivity, resource-constrained environments common in developing regions. Problem statement: technical failures that include aging transformers, lack of continuous monitoring, high maintenance cost, deliberate vandalism, which include theft of copper windings, as well as oil siphoning. Existing solutions are designed for high resource environments, cloud and are cloud heavy. They also include expensive sensors and stable connectivity is assumed. The gap: little or no integrated IoT framework is tailored for African or low resource environments. The aim of this research is to design and validate an IoT machine learning framework that simultaneously addresses predictive maintenance and vandalism detection. The slide summarizes the study's key contributions across architectural design, edge-centric security, security predictive maintenance, as well as real-world validation and cyber physical threat modeling. This slide presents the interdisciplinary theoretical foundation underpinning the study. It integrates cyber physical systems theory, routine activity theory, prognostic and health management, and edge computing to justify the system's architecture and operational logic. Collectively, these frameworks ground the proposed solution in computational intelligence, adversarial threat modeling, reliability engineering, as well as low latency edge processing. Amongst the literature reviewed, the following are some of the gaps that were identified: limited focus on IoT architectures for decentralized grids, as well as minimum attention to African deployment environments. Focused on industrial automation and lacks integration of vandalism detection. Cloud-heavy architectures and little discussion on edge deployment. Limited real-world validation in unstable power and connectivity conditions. The methodology. The slide outlines structured distribution level threat model, categorizing vandalism scenarios such as unauthorized access, climbing, tampering, component theft, nighttime intrusion, and coordinated attacks. It links each threat type to its operational characteristic, corresponding system design implication, demonstrating the proposed architecture is engineered to address time-sensitive, adversarial, as well as high-impact intrusion scenarios. This slide outlines the multi-sensor data collection strategy and corresponding edge pre-processing technique. It distinguishes between high-frequency intrusion signals and low-varying asset health parameters, applying normalization and baseline modeling at the edge. This slide presents a structured multi-stage vandalism detection pipeline implemented at the edge. It progresses from deterministic event triggering to anomaly detection, multi-sensor fusion, local decision-making, and resilient data storage. This slide illustrates how predictive maintenance analytics are integrated into the vandalism detection framework. Time series analysis identifies gradual degradation, while contextual differentiation distinguishes between internal faults and deliberate intrusions. This slide outlines a tiered alerting and data management strategy designed for resilience under constrained connectivity. High severity events are transmitted immediately via priority channels via the MQTT, while low confidence or informal events are queued and batch synchronized. The image on the left shows a pole-mounted distribution transformer installation equipped with a solar-powered surveillance camera. The setup illustrates a real-world deployment of edge-enabled monitoring infrastructure, combining physical asset protection with autonomous power supply. This configuration reflects a practical implementation of digital guardianship, while light self-powered sensing systems are integrated directly at critical infrastructure sites to enhance security, resilience in environments with limited grid reliability or connectivity. While the image on the right shows the internal assembly of an edge-based IoT monitoring unit housed within a rugged enclosure. It integrates lithium-ion battery for backup power, a solar charge controller, a single board computer, communication modules, and wiring for sensor inputs and power management. The results, the operational dashboard shows edge-enabled IoT security and health monitoring system for distribution transformer site. It integrates connectivity diagnostics, GPS tracking, environmental telemetry, motional detection, real-time alerts, controls, as well as time series analytics. The system is designed for remote monitoring of critical infrastructure, combining both predictive maintenance data as well as intrusion or security indicators. This interface represents the visual and geospatial validation layer of the edge-based transformer security system. Snapshot-based camera captures provide event-triggered visual evidence without relying on bandwidth-intensive continuous video streaming, while the GPS map confirms asset location and immobility. This slide summarizes the pilot evaluation outcomes across detection performance, false positive reduction, resilience, operational efficiency, and system viability. The results demonstrate low latency alerting, effective multi-sensor fusion to reduce false alarms, sustained edge node operation during outages, and bandwidth-efficient communication. Collectively, the findings confirm that the architecture is technically feasible, operationally effective, and scalable for deployment in resource-constrained national utility environments. The findings validate the study's central argument, that is, designing systems specifically for vandalism detection requires fundamentally different architecture than traditional predictive focus systems. Security must be treated as a primary design constraint rather than an afterthought within operational monitoring. The study also demonstrates an edge-based architecture enables real-time intrusion detection response without dependence on continuous cloud connectivity. The design is specifically important in developing regions where connectivity is intermittent, power supply is unstable, and operational resources are limited. Integrating vandalism detection with predictive maintenance improves contextual interpretation of asset behavior by incorporating asset health telemetry, trends with the system can differentiate between deliberate interference and gradual internal degradation. The findings also show that effective intrusion detection does not require high compute vision-based systems. Camera-driven approaches are often constrained by high energy consumptions and bandwidth demands, limiting their practicality in remote or resource-limited environments. Limitation: the pilot deployment was constrained in size and observation period. It did not establish long-term impact on vandalism deterrence as well as reliability indexes. Limited multi-season performance. Validation relied on limited manual verification and event correlation. For future work, that is, expand deployment across larger asset populations, study long-term vandalism trends, false alarms, and operational impacts. Explore federated learning for decentralized anomaly improvement and maintain privacy of operational data. Integrate with utility security systems and law enforcement dispatch. Improve coordinated response and reaction time. Also implement adaptive sensing and duty cycling algorithms. In conclusion, this study introduces the vandalism prioritized edge-focused IoT architecture designed to protect distribution transformers in resource-constrained environments. It shifts the focus from traditional predictive maintenance, first monitoring, towards intrusion detection and localized decision-making. The pilot deployment validates the effectiveness of the proposed architecture by demonstrating low latency alert generation, robustness during network outage, and resilience to power disruptions. Integrating predictive maintenance telemetry with vandalism detection enhances contextual interpretation of security events by distinguishing between technical degradation and deliberate interference. The findings demonstrate that predictive maintenance and intrusion detection are complementary and mutually reinforcing rather than competing functions. Acknowledgement. The authors would gratefully acknowledge the support of the University of Zambia, ZESCO Limited, for the institutional, technical, and operational support throughout the research. The authors extend their sincere appreciation to the Ministry of Science and Technology for providing the financial support. And these are some of the references that were used in this study. Thank you.
Thank you for your presentation, sir. I now ask our session chairs if they have any questions for our speaker.
Okay. From my side, there are two questions. Am I audible?
Yes, sir.
Pramod sir? Yes, okay. Which machine learning algorithms are used for early vandalism detections, and why that algorithms are chosen? First question.
For starters, we're working with YOLO version 8. There's desire to also move to another machine learning algorithm, but for now, we started off with YOLO 8. We found that it was easier to implement, especially on the low resource device such as a Raspberry Pi.
And what type of sensors and IoT devices are used for monitoring power distribution infrastructure?
So amongst the devices we're using is a BM sensor. There is a Raspberry Pi, as well as an ISP32 that we have integrated as well for connectivity and connectivity. Apart from those, there's also we're trying to experiment as well with the XD5, though that one has not yet, we had challenges importing it, so we're yet to fully have a go at that one.
Okay, and what are the accuracy, latency, and scalability? What's about these values of your framework?
So latency, we found latency was about it ranged from about 3 to 5 seconds in terms of something being picked up, being captured, stored on the Raspberry, and then transmitted to the dashboard that was shown. So it ranged from 3 to 5 seconds. In terms of scalability, the fact that we're using these IoT devices, it makes it much easier to scale. Currently, we started with 3 pilot sites, but then we've gotten approval to scale to 60 sites so as to see how well the solution will perform. From there, then we'll be guided on how far we can scale it out.
Okay. And what you're thinking about the expansion or enhancing the framework capabilities in future?
Definitely. We are thinking also adding thermal capture, so as to just show, apart from just having that temperature, we also want to see how it's varying in terms of temperature. There's also an aspect that was requested that we increase the range to which the motion can sense. Right now it's about 10 meters. We intend to increase it to about 25 meters. And then with the machine learning, we were instructed to also look out for animals. We need to prevent false positives that are caused by animals. And also we need to look out as well for vegetation. Let's say this asset is located where there's some vegetation or trees that are growing or that will wrap itself around the asset. So we need to watch out for such as well.
Okay, that's okay from my side.
Professor Ruiz, do you have any questions for our speaker?
Yes, I have a question. How do the program detect between natural anomalies like storm breaks or earthquake from vandalism?
Beg your pardon?
So the question that the Professor Mauricio is asking is like, how does the program detect like from natural anomalies like earthquake or storm breeze from the vandalism instance? It's like there are a differentiation point that the machine learning is also is pointing this. Like, what role does it play?
Um, there's a bit of some echo, but I'll attempt to answer. So there are two sides. There's one aspect where we're trying to detect or deter vandalism, where we're using both the motion and the camera. So based on the motion around the asset, the camera tilts to that where there's motion detected and begins to capture using it. It begins to capture images rather than a continuous video stream. Captures the images. Information is firstly cached on the device itself, and then an attempt to transmit to the dashboard is done. And then the other aspect is where we're collecting environmental or the environment conditions around the asset, things like the temperature, the humidity, vibration, so as to also so those parameters are now being used to assess the asset health, where we notice a huge deviation from what has been recorded or has been a trend, then that calls for a need to go and investigate if the transformer is malfunctioning, is having technical issues, or maybe it could be overheating because maybe it has a puncture. It's therefore losing oil. So then there's an alert that's sent to the dashboard via both email and SMS to inform the staff members to now have a look at the asset. I hope I've answered your question.
Fair question.
Thank you. No further question.
Okay, thank you so much for your presentation, sir. We will
Thank you.
now be moving on to our next speaker. So our next speaker is Libero Negro from the University of Calabria in Italy, and the title of the research paper is Clustering Algorithm Based on Density Peaks of Candidate Centroids. So I request you to kindly unmute yourself and start presenting. Hello, sir. Am I audible?
Sorry.
No, it's perfectly fine. You can start.
Can you tell me if a slide are visible?
Your screen is not visible, sir.
Not visible. I just asked for sharing.
Well, let me look into it. Just a second, sir.
You must allow me.
Sir, can you try sharing your screen once again?
System tell me this is loading. Sorry.
It's fine, sir.
It's okay.
Sorry, I couldn't hear you.
Can you tell me if it's okay?
We are still not able to see your screen, sir.
I'm sorry, but I not understand why I have shared my video.
Well, can you try it again one more time, sir?
Yes, I try again. Sorry. Um, sharing and my entire screen. I've made the steps.
Yes, we can now see your screen, sir.
Okay. My name is Libero Negro, and I will try to give some information about our recent project, which concern a modification, a variant of the key means a clustering algorithm. And this is a brief agenda of my presentation. First of all, we try to motivate why we work in improving further k-means. I would recall that k-means is a de facto standard method for unsupervised clustering due to its simplicity but also efficiency, but it has problems. And we try to discuss the basic design issue of our proposed algorithm and tool, which is named density peaks of candidate centroids. We give just a flash on the implementation in parallel Java, and then I will show you, hope to show you several experimental results about reliability and accuracy of the algorithm we have implemented. And then try to give also some direction for the work. Now, I would remember to all that unsupervised clustering aims to groups data point in groups, clusters, through a similarity function. Very often is the Euclidean distance function. And each cluster is characterized that the points assigned to it are similar to each other and are dissimilar if they belong to separate clusters. Each cluster is represented by its central point, which is side centroid. And we have n points, each with supposed with d real coordinates. We have a k cluster. The number k of cluster is supposed to be an input data. And normally, when we do unsupervised clustering, for example, with the k-means, we aim to, our goal is to minimize the sum of squared error, which is a measure of internal variance of point distributions. And I would also recall that k-means basically does the following steps. It starts with a centroid initialization. In the classical method, random seeding method is used in the sense that we choose randomly, by uniform randomly, choose k points in the dataset which are assumed as the centroid. Then we do partitioning in the sense that we assign point to cluster according to the nearest centroid rule. Then we update the centroid of each defined cluster as the mean point of each cluster. And then we check termination in the sense that if centroid is stabilized or a given number of maximum number of iterations have been executed, we stop. Otherwise, step 2 and 3 are repeated. Now, what is important to observe is that k-means actuate as a local search strategy, and it strongly depends on the initialization of centroid. Normally, whatever is the initialization, k-means tends naturally to be stuck in a suboptimal solution. And commonly, the remedy to this situation is to repeat k-means a certain number of times, each time with an independent initialization of centroid, and then the best in terms of minimal SSE measure, the best emerging solution is assumed as the one to use. Now, centroid in reality should be initialized to avoid outliers, error, noise point in the dataset. There should be high density point in the dataset and should be far from each other to avoid that a real cluster, for example, is split in multiple unnatural clusters. Hopefully also cope with the course of dimensionality in this, for example, by using the principal component analysis technique. Now, this picture, which we have taken from Professor Franti's work, it shows that when the initialization procedure associated to a given real cluster multiple centroid, this is a problem because we split a real cluster in a way unnatural. But what is important is that for the local search actuated by He-means, it is almost impossible to move centroid which are in excess in some areas to areas where centroid are expected because they are in defect. So this is a problem due to initialization. Now, in the literature have been considered different seeding methods, some of which are considered accurate. For example, the greedy K-means plus or refine PNN. We all implemented this technique in Java and are usable in our experiments. And this is a list of some measure internal and external clustering accuracy measure. All of this we have implemented in our Java. And just to give you a brief information, we use refine PNN in this experimental work in this paper, and refine basically, which is a modification of the Bradley-Fayad well-known refine initialization method. The dataset is split in a given number of segments, which are filled in a random way by taking points in the dataset, and then we achieve S per kappa cluster, which are systematically reduced to kappa, to k, by pairwise nearest neighbors technique. And each iteration of PNN choose the pair of partition whose margin would increase the SSA by the minimum. Okay, now consider the limitation which we stressed. We designed an approach and a tool which make use both of a genetic elitist approach and use also density peaks, which is a very important technique in the literature for making clustering, unsupervised clustering. In reality, what we do, we organize our algorithm in two steps. In the first one, we build a population with a given number of solutions. We call it elitist because the solutions are achieved by using some existing careful method, for example, refine, or just mentioned the refine. And we have candidate centroid. From the experiment, we observed that although no one solution put in the iteration itself alone can be close to the optimal solution, ground truth. In reality, we observed that many candidate centroid tend to thicken around the ground truth optimal centroid. So in the second step, we use density peaks to identify the most candidate centroid which should be used for feeding k-means. We use k nearest neighbors and reverse nearest neighbors technique to find an estimation of the density peaks of centroid points. And in this case, we, for each point, for each centroid, we detect the k nearest neighbors, we build the corresponding k neighborhood, and then we establish what is the point which is the k distance from a given centroid, and the estimation is based on the identification of the reverse nearest neighbors. The RNN basically uses the concept of friendship in human society, in the sense that the RNN set of a point P is the set of points which have distance which is within the NNK distance of Q. And we in particular compute not only the density, but also we compute the delta and the gamma, the quantity which are important in density peaks algorithms. Delta is the minimal distance to Big Brother, in the sense that a centroid is surrounded. A centroid is a high density point which is surrounded by lower, smaller density points, and the Big Brother is the minimal distance to a point which has a greater distance. Okay, we sort the population by descending gamma, and choose the first K centroid in sorted population to achieve the initialization for K-means. A K-means will refine this solution. In reality, we repeat the second step of applying the KNN, RNN with a given range of K values, for example, from 5 to 150, by step of 5, and thus we create a different generation and choose the best solution. Now, these are much detail. I would only mention that our tool inherits some feature of our recent PAR-DP method we have developed, which is a parallel density peak method, in the sense that from PAR-DP we inherit, for example, the PCA, the principal component analysis technique, trying to reduce the number of dimensions in high dimension in the great dimensioned data set. Here is just an image of to convey in which way we implemented the tool, because we use parallel stream in Java.
Excuse me, sir.
We have finished.
No, I just wanted to remind you, you have 2 more minutes of presentation time left.
2 minutes.
Yes.
This is impossible to talk of technical aspect. Okay, sorry. We made many experiments, and these are some benchmark experiments. And in all these experiments, we achieve very, very careful results. And the results were also confirmed by taking, in this case, which are two-dimensional data set, by building the partition showing what we have achieved from what we should have expected, which are the ground truth centroid of this benchmark dataset. And as you see, red are our determined centroid, red are the ground truth centroid. And you can see that almost in any case we overlap expected from detected centroid. And we also applied the technique to realistic also data set like this. And also in this case, we achieved very good careful results. Also, but I would also stress, by a minimal number of iteration of K-means, because the good initialization we provide will imply that K-means has been executed only for a limited number of iterations. Now, if someone would have more information about our tool, our algorithm, we have just published recently this paper on the algorithm journal, and we call it a genetic elitist approach and density peaks to improve k-means clustering. And in this algorithm, we also compared our algorithm with some competitor implementation, in particular imp k-means and near k-means, which are deemed to be very accurate. And we show that our algorithm perform as these tools, in some cases better than this tool. And the continuation of the research aims to improve the approach by using, for example, random swap in the identification of candidate centroid. And we also would experiment with different techniques to estimate the density beside reverse neighbor, nearest neighbors, and also implementing the tool in other languages like those one. Sorry for my English. I will thank you for your attention, and sorry if I have used more time than assume the time for presentation. Thank you for your attention.
It's absolutely fine, sir. I now ask session chairs if they have any questions for our
Yes,
speaker.
sir. Can this algorithm handle the high dimensional data?
Please,
Can your algorithm handle the high dimensional data?
you would ask if we have data about our algorithm.
Sir, he
What
means
do
to
you mean?
ask if your algorithm can handle high dimensional data.
High dimensional. Oh, yes. For example, consider this very hard data set, which are worm-like data set. And for example, this data set have, sorry, just a moment, have 105,000 points. You understand that these are very big normally. And for example, the second one has 64 coordinates per point. So it is a high dimensional. And our algorithm also, for example, suggests us that through the PCA, the number of effective coordinates which are relevant for the variation, for the statistical variation of the point distribution. For example, in worm 64, all the 64 are relevant. For the worm 2D,
yes, sir. Okay.
Please.
Yes, sir. Okay. Thank you. I got.
Thank you.
Okay. That's okay from my side.
Okay.
Professor Ruiz, do you have any questions for our speaker?
I have no question, but I want to congratulate you for this research.
Thank you very much.
También quiero decirle algo un poco ya más en mi idioma. Ian, colabórame, porfa.
And so Professor Mauricio says that he wants to tell you something about that more in Spanish. So I will be translating also.
Sure, sir.
Me pareció un muy buen aporte debido a que pues yo he usado mucho también el algoritmo Camins y pues siento que existen ciertas limitaciones y veo que es un gran avance.
So Professor Mauricio says that he has used the Cummings model and he wants to thank you because he sees that this research is a great way to overcome those limitations that we face with the Cummings model.
Invitándolo a seguir invitándolo pues a que siga haciendo experimentación y tratando de generar estos avances, la verdad que son mucho más tecnológicos y que en la práctica pues nos ayudarían mucho a los investigadores.
And he also says that he encourages you to continue making this research because it would be really helpful to people such as himself who use these type of models to continue to make advancements.
Sorry, what is the question? Sorry.
Oh no,
No, sir,
it
he
was
wasn't
no.
asking you a question. He was just congratulating you on your research, and he
Oh,
also said,
sorry.
"Oh, it's absolutely fine."
I have heard about limitation. Obviously, this is not a perfect solution. Obviously, it is a human solution which try to improve some existing method. And in our approach, we have found that by taking similarity of candidate centroid, we can better initialize k-means, and from the experimental result, this is promising. Only this I can stress this. Thank you
Okay,
for
sir.
the observation and attention. Thank you very much.
Yes, thank you so much for your presentation, sir. We now quickly
Okay.
move on to our next speaker for today. So our next speaker is Inas Ismail Imran from the University of Information Technology and Communication in Iraq. And the title of the research paper is Leveraging Attention-Driven GANs for High Fidelity Text-to-Face Image Synthesis. Ma'am, I request you to kindly unmute yourself and start presenting.
Hello, everyone. Let me share the screen.
Sure, ma'am. Just a small reminder for all our speakers today, kindly adhere to the time limit so we ensure a smooth flow of events. Thank you.
Okay, the presentation is appear. The
Yes,
presentation
ma'am.
is
The
appear.
presentation is visible and you are audible as well, so you can start presenting.
My name is Inas Ismail Umran. I'm a PhD researcher at the University of the Communication and the Technology and the Communication Informatics Institute. My paper is leveraging attention-driven GAN for high-fidelity text-to-face image synthesis, supervised by Prof. Dr. Ahmed Abdulsahib Hashim. First, we are talking about introduction the generative model overview. First, we are talk about the GAN and what is the generative adversarial network and the text to image generation. What is the aims? The aims to generate the photo image which are semantically consistent with the text description. And the deep learning has advanced image synthesis across the design, media, and augmentation with the GAN enabling high fidelity generation via adversarial training. More recently, diffusion and transformer-based model have improved the text-image alignment, yet the text-driven face synthesis remain difficult due to the price attribute localization, example expression, hair, accessories, spatial coherence, and identity preservation. The recent work show complementary strength between the GAN and the diffusion model. The GAN-based model enhance attribute localization and the texture realism through spatial alignment and diffusion technique, while the diffusion approach offers strong control and identity retention through across attention. This study reports attention-driven conditional GAN, AD, CGAN for high-fidelity text-to-face image synthesis, generating photorealistic human face from semantic facial attribute that suggests model conveying attention and probabilistic condition method in order to obtain the accurate semantic alignment and improve realism of perception. What is our aims and contribution? These papers present leveraging attention-driven GAN for high-fidelity text-to-face image. And to reduce attention-driven conditional GAN that convey condition augmentation, multi-scale, cross attention and the self attention to improve diversity, attribute control, and global facial consistency. The main contribution are unified attention guided conditional GAN using multi-scale cross attention plus self attention for improved semantic correspondence and spatial coherence. The second contribution, condition mutation to adjust the text embedding and increase control variability. And the third, stable WGAN GB training with the comparison evaluation protocol combining quantitative RMSE, BSNR, and SSIM, and qualitative analyze visual comparison and attribute interpolation. Together, this innovation will help to build the model that are control the text-to-face generation and that is suitable in realism and computational cost. The related work, we study the related work. There is the feature-wise comparison of the ID GAN with a selected GAN-based text-to-face synthesis method. These are the method are used, and we compare our work with this method. The method as phase GAN, the condition type, text attribute, special mask, and the attention type, word label, and special attention use landmark training objective GAN variant and the key strength, strong attribute localization, and the limitation in weaker global coherence. The second is LGIF. It uses paired embedding and the style GAN mapping. The attention type, attention and latent mapping use landmark and the style GAN, the training objective, style GAN base. And the key strength is high visual realism, and the limitation is deterministic condition. The LB-GAN, it is used the condition type, the text that facial landmark, the attention type, co-attention with the structure pairs, use landmark, yes, the training objective GAN variant, and the key strength, identity, and the detail preservation, and the limitation require landmark pipeline. And this is our, at last, our ID, attention driven GAN, C-GAN, it uses condition type, a probabilistic condition of mutation, and the attention type, multi-scale cross attention plus self-attention, use landmark, training objective, WG GAN, GB, and the key strength, stable training and control synthesis, and limitation limited by 64 by 64 resolution. We are talking about the proposed model. We are begun with the data equation as we see in the figure. We are begun with the data equation stages where the facial where the facial image are connected and pre-processing, and then we have the input stage. The model received two main components: the text attribute describing facial feature and the random voice factor. And then we apply the condition of mutation CA, which is used to the text encoder that extracts semantic feature from the text description. The CI network then generate condition factor from the text embedded. The condition factor together with the noise input is fed to the generator. The third step is the generator. The generator is attention-based and produce synthesis-based image and integrated both text attention and the self-attention as we see in the figure, and the spatial consistency. The generated image along with the corresponding text is then go to the discriminator. The discriminator is compared between the real image and the fake image by downsampling the CNN combined with the encoder, text encoder, and then during that training, whatever it is image and distinguish whatever is image is real or sorry, whatever image is real or fake. And then we have the output, the training with the W GAN is GB, the plus KL convergence, which is improve stability and semantic condition, and the output is high fidelity text alignment image. Then the evaluation we are used in our model is RSME, RMSE, BSNR, SSIM, which is a matrix that is cover high fidelity text, face image, and consistency with the semantic image. The data equation and pre-processing. The data equation and pre-processing, the study use celebrity A. We use the data set, the celebrity A, which is one of the largest the data set, and we have to accrue our image to the 64 and the 64 normalization and normalized to the -1, and the attribute label binarized from the -1, 1 to 0 and 1, and then we are using the trainings of the 64 sample, enabling the stable and efficient learning from the ICICT. This is the table to show the feature and the description of the use. The total image is were used is 2,599 alignment and group with a face image. Then we use is notated. Then the user identity is 2,177 unique individual, and attribute that are we use is 40 binary facial attribute, and the facial landmark is the 5 point are it is nose, mouth, concern, and the eyes. And the source of this data set is from Lab, the Chinese University of the Hong Kong. We have the generator and the discriminator. The generator and the discriminator. The generator algorithm, as we see, is work as take a clean mean input, the 100-dimensional input, and the noise spectrum, and to introduce diversity, and the 128-dimensional, that is condition factor from additional control, and the 256-dimensional text embedding
Excuse
that
me,
is
ma'am.
called. Yes.
I'm really sorry to interrupt, but I just wanted to remind you that your 10 minutes are over and you have 2 more minutes of presentation time left.
Okay.
Yeah,
Okay.
thank you so much.
The idea of the generator is begin with a small image features 44 by 4, and then begin, and then until we are done to the 64 by 64 using deconvolution. Then we upsample to the 32 to 64, and then the discriminator is to, as we said, is to distinguish between the real and the fake image. The discriminator begin with the dimensional 64, 65, 64, and then it is down sampling to the 4 is the letters of the generator. The training, as we see, the training model, as we see figure, the discriminator rules, were generator rules, and key KL divergence rules. This figure that shows the epochs, the discriminator rules stabilize after early fluctuation, and the generator gradually improve on the KL diverge, converge smoothly, indicating effective condition equalization and balance W-GAN GB optimization. And this is the generated custom image that are model for, as we said, for it is use 50 epochs and is used for the resolution 64 by 64. The image quality evaluation, we use three metrics to evaluate our model. The metrics is RMSE and BSNR and SSIM. The table show these metrics and the metrics have these metrics achieve zero. These metrics achieve RSM of the 0.3383, indicating moderate pixel level deviation between generated and grounded truth image, and then BSNR of 9.665 gives acceptable single to noise ratio, and then the RMSE 0.3383, which is indicated moderate consistency and facial structure. The table comparison of the related method and their key limitation highlight why the proposed attention-driven GAN is provide advantage. The method we are compared is, as we said in the related work, SS-based GAN. Key limitation is limited global coherence, why our method is better, adds potential for long-range consistency. The LGAR deterministic condition use probabilistic condition limitation for diversity. FLB GAN depended on landmark, no structure pair required. Diffusion, high computational cost, lightweight GAN, our method lightweight GAN-based alternative. The conclusion, we said our model is to achieve a real face from the text and the control of the text. This is our model, and we have a multi-scale attention using W-GAN and the GB training to generate semantically consistent and realistic faces with this inception score, and we use inception score IS providing control and semantically grounded assessment of realism, diversity, and distributional similarity between generated and the real face image. The success, as we said, we have three measure metrics, SS, RMSE, and the BSNR, and the SSIM, which is evidence of the retrained global structure in low resolution synthesis. Thank you for the listening.
Thank you
Any
for your
question?
presentation, ma'am. I now ask our session chairs if they have any questions for you.
Madam,
Yes.
how does the model handle issues like identity preservation, expression, and pose variation?
The model for the resolution is
Issues identity preservation.
The style GAN is better from all the GAN. It's style GAN. It's give a good resolution, and also the give. But we are talking about the C GAN, which is the best on the condition. The text with the GAN, where it's the better is for the resolution is the style GAN, and we use it in other research, and it's give good quality image, and the feature is good. Also, it is a very the feature no blur and no artifact features.
Okay, thank you.
Thank you.
Professor Ruiz, any questions for our speaker?
Te están preguntando así.
Yes, I have a question. What
what strategy use anyway. What future developing or improvements do you envision for the research in the coming years?
Sorry, I couldn't understand your question.
Ma'am, he means to ask you about your future work or what you are planning to do ahead.
Yes, the future
Yes, yes.
work, our model is using the data set, and it is apply on the 64 by 64. Our future will the resolution should be more to 600 or better resolution, because our model is low resolution image, as we said, is 64 by 64 image. And we can use the model to large image resolution to better quality image.
Any more questions, Professor Ruiz?
Yeah. Any question?
Okay. Thank you so much for your presentation, ma'am.
Thank you.
We now move on to our next speaker for this session, which will be Bashir Abdullah Al Saidalani from the Talaba University in Saudi Arabia. And the title of the research paper is Lightweight Fine-Tuning of a Transformer-Based OCR Model for Arabic Historical Manuscript Recognition. Ma'am, I request you to kindly unmute yourself and start presenting.
Okay. Can you show my presentation?
Yes, ma'am, but your voice is a little bit low. Can you speak a little louder, please?
Okay. Now can you hear me?
Yes, ma'am, I can hear you just fine. You can start presenting.
Okay, good evening, everyone. My name is Bashair, and I present our work titled Lightweight Fine-Tuning of an Transformer Based on Optical Character Recognition Model for Arabic Historical Manuscripts Recognition. Author Bashar Sadalani and Hanoud Al-Haysuni, Liako Tunisa Sayed from Taiba University. In this works, we focus on improving recognition performance for historical Arabic manuscript using an efficient fine-tuning strategy. Now I will briefly outline the structure of this presentation. The presentation is organized as follows. First, an introduction, then the problem statement. After that, the methodology overview, followed by the quantitative result, and finally, the conclusion and future direction. Let's us begin with the introduction. In that introduction, Arabic manuscript represent a rich intellectual heritage spanning more than 14 centuries, covering science, geography, literature, and many other fields. Digesting this manuscript is essential for casual perception and scholar accessibility. However, Arabic script itself introduces a technical complexity. It's written right to left, highly cursive, and letter change shape depending on the position in the word. In addition, many letters differ only by diacritical marks. A historical manuscript added another layer of difficulty, include faded ink, bleeded through, and irregular illumination. This factor collective make recognition highly challenge. This leads us to core problem. A current handwritten recognition benchmark as CAT and Huda focus mainly on modern handwriting. When we pre-train this model, developed on a modern dataset, are applied a historical manuscript, performance drops visibly. This is due to noise, statistics diversity, and domain mismatch. As a result, we observe increased character error rate and word error rate. Therefore, the key question becomes how can we improve modern optical character recognition model efficiently to historical manuscript under limited data condition. To answer this question, we designed the following methodology. Start from data collection, then image pre-processing, then line segmentation. After that, data augmentation, then move to optical character recognition model fine-tuning, and finally, recognition and then evaluation matrix. Each stage is designed to address a specific limitation in historical optical character recognition. No, I will explain the dataset and the pre-processing stage in more details. About dataset, the manuscript used in this study is الأدريسي نزهة المشاق في اختراق الآفاق, obtained from the Qatar library, digital library. For pre-processing, we applied grayscale and median noise filter, also global thresholding and adaptive thresholding, DCQ correction, and constraint enhancement. This step improve readability and reduce background noise before segmentation and training. After pre-processing, we move to segmentation. In segmentation, we develop a Python code tool to detect horizontal text region based on pixel intensity. The original dataset contains only 200 lines. This is insufficient actually for training a transformer model. Therefore, we applied augmentation by replacing image using control transformation while preserving label. This increased the training set to 644 image. With the expand dataset, we proceeded to model fine-tuning. We use a lightweight. We updated only the upper transformer layer and the autoregressive text decoder. The visual encoder remained mostly frozen to retain general optical character recognition knowledge. The model used in Queen 2.5 version series. This model is used in visual understanding and generating stable textual output. This selective adaptation reduces contextual cost while enabling a domain alignment. Now let us examine the result, quantitative result. This chart summarizes we evaluate performance using character error rate and word error rate, character and word and sequence accuracy. No, I will present. No, I will present the exit numerical conversion for this baseline achieve 17.82, but in our fine-tuned model achieve 16.49. In word error rate achieve 48.14, and chair accuracy 83.51, and the word accuracy 51.86, and sequence accuracy achieve 5.13. Also, we compared against the external Muharraf model. You can show a number of results. Fine-tuning nearly doubled the sequence accuracy compared to the baseline. This confirmed that lightweight adaptation improved domain-specific performance. However, numerical improvement alone doesn't explain the error behavior. Let's move into error type distribution. We categorize recognition error into three types. Substitution represents 64.9% of error. This occurs when the model predicts the wrong character. Insertion represents 21.9%. This occurs when extra characters are added. Deletion, this occurs when characters are omitted. Most confusion occurs when letters sharing the same base shape but different in dots, like a group 1 but third different from just a dot, group 2 جيم ح خ, and group 3 فا قاف. This indicate that dot discriminal remain a major challenge. Now I will show an example from the testing phase. Simple from testing phase, this slide. 40 يوما بسير القوافل وأقرب البلاد إليها من بلاد لم تونة. When you say 40 شبه الهمزة we omitted by القوافل replace فا to القاف, then you show it. We can observe that most errors are related to visual similar character. The best remain the fine-tuning model produce a structure output. Now I will conclude. In conclusion, lightweight fine-tuning is a feasible and efficient solution for hostile manuscript optical character recognition. Without domain adaptation, modern models cannot replay generalized to manuscript. For the future, inshallah, we plan to apply linguistics post pre-processing to correct invalid word prediction, and also aim to expand the dataset with more diverse regional calligraphy styles. Thank you for attention and listening.
Thank you for your presentation, ma'am. I now ask our session chairs if they have any questions for you.
I have a question, please.
Yes.
Sure, sir.
Hello.
Yes, sir.
Hi.
Madam, this model is only for Arabic language, no? Hello.
Sir, you are audible.
Am I audible?
Yes, sir, you are audible.
Yes,
My question is that this model is only for Arabic. Okay.
Yes, for Arabic language, historical manuscript.
Why you chosen only for Arabic? Then you use the good results. Then why it is not for the some other similar language, similar group of languages?
Because the Arabic have many issues and a challenge in the manuscript, historical manuscript. Then folks of can extract science from this manuscript. We can focus on this language, and then in future work can expand the region of this model.
Okay. This is your PhD, your postdoc research work.
Sorry, I don't understand.
He means to ask if this presentation is a part of your PhD research.
Graduate.
Yes.
Master research, yeah.
Okay, thank you, ma'am. Professor Ruiz, you can now ask your question.
Yes, the question is, did you use the model Wagon training manuscript, and how does it work?
Sorry, I don't understand.
Sir, can you please repeat yourself?
Yeah, so what Professor Mauricio was trying to ask is like if you use the model or your program with untrained manuscripts, and how was the performance?
We use a pre-trained model from Queen series, just update a lower upper layer of transformer, then performance high, actually like 1.5% from baseline and our fine-tuned model.
Okay, thank you.
No further questions, right?
Yeah, that's correct.
Okay, thank you so much. We can now move on to our next presentation for this session. So our next presentation will be done by Tan Guen. I am really sorry for any mispronunciations. from the Duy University in Vietnam, and the title of the research paper is MDS Diffusion on Quantum Hardware, a literature review. Sir, I request you to kindly unmute yourself and start presenting.
All right, hi everyone. Make sure you can hear me very well.
Yes, sir, you are audible and your presentation is visible as well.
All right, it's good to hear. All right, so good morning, everyone. This whole study about how MDS diffusion layer, the kind used in AES and many SPN design, can be implemented as quantum circuit effectively. The focus is the diffusion step, not a full cipher implementation. The goal is to understand what it means to treat a diffusion like a reversible linear transformation and what existing synthesis method to imply for gate count, depth, and qubit overhead. Okay, on the cryptography side, the diffusion layer, especially the MDS matrices, are designed to give probably optimal spreading of byte activity in AES, as you can see in here. The role is played by mixed column and its inverse. Highlight in the diagram, these layers are traditionally implemented as a matrix multiplication over Galois field 2 by 8, power by 8. And classical efficiency is usually discussed in terms of field multiplication, XOR count, and implementation structure, as well as some other, such as time complexity in doing the matrix multiplication. So on the quantum side, the thing is, the viewpoint is a little bit different. Quantum gates are linear operators by themselves, so linear diffusion layer can treat it as a matrix transformation on qubits and compile into reversible circuit, typically a network of CNOT and swap gates. Optionally, the redundant qubit can be used at the depth space objective. This motivates a different kind of efficiency, not classical multiplication, but like some like gate count, circuit depth, and qubit overhead. So let me move past the MDS design in cryptography. So we introduce the MDS diffusion in AES setting. Diffusion ensures that differences of our linear mass do not remain localized. The standard diffusion metric can be named as a branch number, the minimum over all non-zero input, or the number of active symbol in the input plus the number of active symbol in the output. Here symbol are bytes in AES. For a square matrix n by n linear over a finite field, the best achieved branch number is n plus 1. A matrix that achieves this bound is called MDS, meaning it provides optimal diffusion at symbol level. A key equivalent characterization used in diffusion design is every square submatrix is also non-singular. AES mixed column is canonicalized by example. Multiply each 4-byte column by a fixed 4x4 matrix over Galois field 2 power by 8. Since n is equal to 4, the maximum, the optimum branch number is 5 because n plus 1. And mixed column is designed to meet that bound. So activity is spread quickly across bytes. For quantum equivalent and quantum oracles, this matter because diffusion become a reversible linear transformation on the qubits. Even though it's only linear, MDS matrices tend to be dense, and the bit level expansion become dense and binary matrices. So the synthesized CNOT network has meaningful costs in both CNOT count and depth. So let's see how how we can construct a MDS matrix. The first method is called Van de Mont, and they often be used as a generator of Reed-Solomon code. So we start by selecting distinct finite field. The Van de Mont matrix is built from this point. It's invertible because the determinant is a product of all pairwise differences, which is non-zero when all points are distinct. However, the invertibility in this context does not guarantee MDS condition. To guarantee the strong O minor singular property, we often use a generalized Reed-Solomon code. I mean the generator matrix, which is a scale van der Waals where each column is multiplied by a non-zero weight. So for the diffusion design, transform the generator in here in this form. The resulting matrix A inherit the strong minor structure needed for MDS diffusion and achieve the optimal branch number k plus 1 at a simple level. But we have a better way to generate MDS, which is Cauchy matrix. I mean Cauchy method. So we select two sets of finite field so that within each set are distinct. We can define the matrix entry as such. The determinant has a closed form involving product of pairwise differences between the x and among the y divided by the product of all differences between x, y. So under this condition, the crucial point is stronger is that these are non-zero distinct constraints. C is invertible. So when we obtain the MDS matrix, we have to translate it into quantum circuit. How do we do so? The first baseline method is called Gaussian elimination. So after expanding the field into bits, a diffusion layer becomes invertible binary linear transformation. The in-place quantum operator map every n by n matrix into n qubits. The fundamental correspondence is that the C0 gates perform an XOR from one qubit to another. That is exactly the elementary row at operation. So Gaussian elimination becomes a compilation procedure. We apply row at step to reduce M into identity, record them, and map each C0, each operation into C0. Because M is invertible, this can be done in place and typically without any redundant bits. So naive elimination can be gate heavy. So a standard refinement is that the Patel-Accord and Hayes approach reduce the C0 count by choosing elimination strategies and the composition more carefully. So for the mixed column AES, once the 4x4 matrix over GF to power by 8 is expanded into 32 by 32 binary matrix, optimized styles for around 90 C0 gates, provide a concrete baseline for the in-place and of the MDS diffusion operator. And this is also the way how ICICT translate the matrix into a quantum circuit. So it can be used in industrial libraries. So for linear reversible circuit, minimizing C0 doesn't count as a guarantee the minimum depth. On the early hardware, deeper circuit accumulate more noise and decoherence. On fault-tolerant system, however, the depth translate into time step, and in quantum crypto analysis, a oracle is repeated many times, so having an even fewer layer per diffusion can have some significant savings. So gradient heuristic depth optimization method can modify elimination instead of fixed elimination order. They select C0 operation that cancel many ones in the matrix without while also enabling parallel scheduling, meaning C0 in the same layer act on disjoint qubit resources as much as possible. These methods are often achieving large depth reduction without using redundant. So oh wait, well, I haven't done yet. In place. Okay. A concrete benchmark is that AES, a mixed column depth-oriented synthesis can produce the anisilla-free circuit with depth around 10, improving earlier depth record were notably larger. We have seen the previous one is around 90. This typically comes with small CNOT count trade-off compared to the most gate minimal circuit, but it provides a practical option where depth is primary bottleneck. Now we switch to the out of place computation. This is where like things got more interesting because we use more qubits in the trade-off for time it use. So for out of place, preserve this input and write the result into a clean output register. The most direct implementation might mirrors algebra. Each output bit is XOR of a
Excuse me, sir.
Yeah, 10 minutes.
I'm
I
sorry
know.
to interrupt. I just wanted to remind you that you have 2 more minutes of presentation time left.
Yeah, that's what
Right.
that only I need. Yeah, all right.
Sure. Thank you so much.
The idea is to reduce that by allocating workspace qubit or partial XOR sum. Instead of accumulating a long XOR sequence into output qubit, the partial sum are formed in parallel using XOR trees, reducing depth from linear to fan in the fan-in algorithmic output are then assembled from these partial sums. If this circuit is part of larger reversible computation, the redundant qubit must be uncomputed back to zero, so no garbage remains. So from a theoretical perspective, the additional qubit change what depth class into achievable with sufficient workspace. Linear circuit can be compressed into toward O log n depth without those additional qubit lower bound prevent such aggressive compression for general linear maps. Practically, this becomes a measure of qubit for time check. A representative mixed column comparison illustrates the magnitude. An in-place circuit can be relatively deep depth, while in the other form, its heavy out-of-place design can be reduced the depth dramatically. So for the research gap and direction for future work, first there's a mismatch between how diffusion layer are designed and how well they are synthesized. Cryptographic diffusion layer are often structured in circular form, recursive, or specialization of the Cauchy matrix. But in here, while translating into quantum counterpart, we don't often have a study into how these structure can be optimized. Secondly, results can be hard to compare because cost reporting is not standardized. Some work emphasize the not count, other in depth emphasize in depth. Third, hardware realism is another thing to consider because well, we don't have any up-to-date commercial quantum device just yet. Finally, benchmark coverage is narrow. Mixed column is widely used as a reference, but there are limited systematic benchmarking across different MDS structure. And that should be the end of my presentation. If you have any question, please ask me. Yeah. Anyone?
Hello, sir. Am I audible?
Yes. Can you still hear me?
Yes, we can still hear you.
Yeah.
Please go ahead.
We move past from my presentation, and that was the end of it, which is a research gap and direction for future works. Oh, wait, there's another slide. Is my work cited?
Oh, okay, sir. Well, I now ask our session chairs if they have any questions for you. Dr. Bakchore, am I still audible?
Yes, sir. Yes, sir.
Sir, do you have any questions for our speaker?
No, sir. As it is
Okay.
said by people.
Okay. Professor Ruiz, any questions for our speaker?
For us, me and Professor, we do not have any further questions.
Oh, okay. Thank you so much. Thank you for your presentation, sir.
All right. Thank you, everyone. So I will stop sharing my screen from here.
Sure, sir. Well, we now move on to our next presentation for today. So our next presentation will be done by Tien Son Pham. I'm really sorry for any mispronunciations, but he is from the University of Science in Vietnam, and the title of the research paper is Software to Hardware Design of a TZS-based IME Accelerator for VVC, VTM, and FPGA. Sir, I request you to kindly unmute yourself and start presenting. Sir, am I audible?
Okay, now I will share the screen. Yeah,
Your screen is visible, sir. You can start presenting.
okay. Hello everyone. Good day. Today I am here to present for the topic software to hardware design of textual source by integral motion estimation accelerator for versatile video coding, VTM, and FPGA. The author me Tiến Sơn Phạm, Tấn Phát Đạt, Quang Anh Nguyễn, Hữu Thuận Quỳnh. I am main presenter today. I am a research student from Faculty of Electronics and Telecommunication, University of Science, Vietnam National University, Hồ Chí Minh City, Việt Nam. Below outline of my presentation. Introduction, conventional texture algorithm, research web, contributions, global hardware oriented texture integral motion estimation architecture overview, coding efficiency on VTM 15, FPGA implementation result, conclusion, reference, and finally the Q&A session. Now I come to the introduction. Versatile video coding, VVC, achieve around 50% bitrate reduction over high efficiency video coding, SEVC. However, computational complexity increased substantially, and the integral motion estimation, IME, account for from 40 to 60% of the total encoding time. What 3 multi-type 3 QTMT partitioning and 1 to I time 1 to I coding tree unit CPU also significantly increase the IME complexity. So what does the integral motion estimation do for? The IME search for the best margin reference block for each current block, and the input search parameter is search range, search window, and search area. The output is motion vector, MV. This regression displacement from the original predicted position. The main aim is to minimize the ray distortion cost. The ray distortion cost equal sum of absolute difference plus ray cost, where the sum of absolute difference is the matching distortion between the current lobe and the reference lobe. The ray cost penalize the motion vector signaling with respect to the predicted motion vector. So how about the integral motion estimation in VVC? The VVC increase the IME complexity due to QTMT partitioning 1 to 8 times 1 to 8 CPU and the large diversity of variable block size VBS. So it comes to the result: more coding unit, more CU, strong inter-CU dependency, and the higher hardware implementation difficulty. So we come to the conventional test search algorithm. The test search is the algorithm used in VVC test model, VTM, and it has 4 stages. 1. Predictive motion vector initialization. 2. Diamond search, and plus 2 point search with a specific condition of best distance D star equal 1. 3. Raster search. 4. Refinement search, also plus 2 point search with the same condition best distance D star equal 1. So the ranking nature complicate hardware implementation. So on behalf of order, able our knowledge, we test that have a research graph. The test shown by integral motion estimation for VVC remain underexplored. So we have 2 key hardware challenges. 1. Multi-stage ranking search flow, diamond search, then raster search, then refinement search. There's many steps. 2. Strong inter-CU dependency limits the balancing and parallelism. So we order have to do we want to do some contributions. First, hardware hardens data magnetics tangential scalar and 4-way mesh connected processing element array with high reference data yield, parallel QTMT VBS processing, and we do that. And we also do end-to-end validation on VTM 15 and on FPGA prototype. This is our robot hardware-oriented test search. We formulate the test search algorithm into 3 deterministic states. Stage 1, we merge the predicted motion vector, diamond search, 2 point search into 1 state, and we start from 0 point. Stage 2, if the CTU level best distance D star is more than raster try, we trigger the raster search. Stage 3, we unify the refinement and 2 point into the 1 state. We find the best motion vector until the best distance equal 0. So the benefits is deterministic control flow and parallel evaluation. We can see the main concept of our robot hardware-oriented test search in the figure. So now we move to the integral motion estimation architecture overview. It's 4 module group. A memory subsystem here for reference block memory, current block memory. The control unit here is to generate the bond and generate address. Here the core data bus. This is processing element array, addr tree, comparator, and the array cost module here is fully data parallel architecture. With the processing element arrays, it's a 16 times 16 mass processing units PU. And SPU compute 4 times 4 sum of absolute difference. With the 1 to A times 1 to A CPU, we split into 64 times 64 regions. And this architecture approximately 98% reference data reuse because only one new round or one new column is loaded per candidate. This is hierarchical by line address. It's 10 state and it's accumulated from 4 times 4 up to 1 to A times 1 to A. It also supports 62 times 1 to A and 1 to X times 64. It's parallel QTMT block size evaluation. Now we evaluate the coding efficiency on VTM 15. We use the standard configuration with 13 standard C1. The quantization parameter are 22, 27, 32, 37. Low delay P configuration. First 100 frame. And the average result here for the PDBR is minus 0.17%. For the PD signal noise ratio is plus 0.01 decibel. So with this result, our robot algorithm maintain the coding efficiency compared with the original test source. Our architecture is designed and implemented on the FPGA. We use the platform Silent S3 Test 7, SC7VS4A5T using the Vivado 2024.2. And this is the resource usage. Totally 139,412 lookup table and 222,002 register and 25 BRAM. The max frequency we can reach on the FPGA is 147 MHz. This is the comparison between our work with earlier work. And we also compare between VVC with earlier VVC and with SEPC. Also compare between test shot and full shots. Both on.
Excuse me, sir.
Yes.
Just a reminder that you have 2 more minutes of presentation time left. Thank you.
Okay, thank you, sir. The same FPGA platform Verter 7. Our work block size is 1 to A times 1 to A size, and the short area is 256 times 256. We on our work have the robust with a resolution of 8K with 28 frames per second. So this is our conclusions. This is the data mathematics hardware-oriented technical search. It's match connected highly yield processing element array. And it's did by line hierarchical arbitrary. It's parallel QTMT VS evaluations. And with this, we have the result, the coding efficiency result with this result. And we also can get the resolution 8K with 28 frames per second on this VTEX 7 FPGA chip. Here is our reference used during my presentations. I keep the same order with the paper. Okay, thank you for the attention.
Thank you for your presentation, sir. I now ask our session chairs if they have any questions for you.
Yes, sure.
So my question is, what are the implications of this work for real-time video encoding applications?
Yes, correct. With the result of resolution of 8K with 28 frames per second, we can meet the real-time video encoding application. Yeah, for real-time video encoding.
Dr. Vakchore, any more questions for him?
No, sir. Thank you.
Okay. Professor Ruiz, any questions for our speaker?
No question.
Okay, thank you so much, sir. Thank you for your presentation.
Okay, thank you everyone. Thank you, sir.
Well, that brings us to the end of our session for today. I now request our session chair, Dr. Vakchore, for his closing remarks.
Okay, sir. So first of all, I would like to thanks to all the speakers for their insightful presentation and the audience for these engaging discussions. I also thanks to Amog Damde Research for their nice anchoring. Then from this session, I will tell you that the one algorithm, clustering algorithm proposed by the Ribeiro Negro sirs. So that is very nice research I found. Also, Inas Imran Ma'am also presented her work. That is also innovative research work, as well as the combination of from software to hardware by the TN Sohn Farms is also very nice. All the presenters are presented their work, research work very nicely, and definitely the thank you to all participations, and the definitely enjoy the rest of conference. And I also happy to work as a session chair for such a nice research work presenters. So thank you and all the best for the conference.
Thank you so much, sir, for your kind words. I now request Professor Ruiz for his closing remarks.
So, in behalf of Professor Mauricio and myself, want to thank you all for your presentations and your research. Every research was very intelligent, very nice, very intelligent. Also, we love it the fact that it was really tech oriented, a lot of details onto it. And we see that each research have like a very future, very potential more outcomes in the future. So we want to congratulate you all for your nice work to continue work on. And also for the ICICT 2026 for have us here. And we hope that the good works continue and see you next year, let's hope.
Thank you so much, sir. I sincerely thank all our authors for their excellent presentations and contributions in this session. and also all of our participants for being a part of this conference. I hope this session was informative enough for all of us. And on behalf of the entire team of ICICT, I thank all of you for your support during this 11th version. And we will be more than happy to host all of you for the 12th version in 2027 as well. A quick announcement for all the presenters. You would be getting your digital certificates via email within 2 working days, and the publications will be live within 7 to 8 months. So kindly cooperate with the team of ICICT. I also thank both our session chairs for chairing this session. This is just a small token of our appreciation on behalf of Team ICICT. A kind request to all of you, can you please switch on your cameras for a quick snapshot of this virtual conference?
एक सेकंद था.
Give me just a second. Yeah, so that is all from our side. Thank you so much for attending this session. Stay safe and take care.